And if you make that assumption, it would take 1.8 million years to colonize the entire galaxy, which is not a long time.
No. Assuming that your spacemen or space women can live that long, actually, to go across between stars.
Space machines, right? They'd be space machines.
You sent your frozen people, or more likely, you send fertilized eggs, frozen fertilized eggs, and compute and get them to wake up when it finds a habitable star, a planet. We're live again. Okay, so we've got to be careful what we say now.
I mean, what I would do is I would send like 1,000 soup can size self-replicating machines, in the hopes that one of them will successfully touch down, and then you beam your civilization into that self-replicator, and then the whole thing repeats.
Yeah, but Ivan, that successful little spacecraft that has found a habitable planet has to send a signal back to you, back to us, right? And we're a very long way away, so it needs a huge power to send anything back to us. So so that's the the answering problem. How do they tell you we are here? Because
remember a few weeks ago, Scott gave me the assignment to calculate how much resource it takes to listen to radio signals from Earth.
All right.
And I did the calculation for an FM radio station operating at max allowed effective radiated power. And if you put the big Chinese radio telescope, the half-kilometer dish, on Mars, when Mars is on the same side of the sun as the Earth, you could hear an FM radio station from Mars at the time when its rather flat radiation pattern happens to be pointed to Mars, because of course the FM stations adjust their antennas so that they're transmitting along the surface of the Earth. They don't want to waste power beaming up higher. And then the size of the dish grows linearly with distance. If you wanted to have a dish at the distance of Proxima Centauri, you need a dish 5 times the diameter of the Earth to be able to listen to your local
holy cow
to your Chicago radio station.
Yeah,
125,000 miles or so between friends.
Yeah. So
also, when we're talking about that, so SETI, listening to see if we can hear radio signals from another civilization. I mean, it's a fun project, but the chances about 10 to minus 10 or something, because the one thing, this famous Frank equation, but it says how part of that is how long do advanced civilizations actually continue to use radio as a means of communication and beam radio waves. And it's been over about 100 years for us out of a total of 13 billion years ago. So maybe in 100 years time we won't be using radio much anymore.
Well, the SETI idea presupposes that there is some extremely low entropy signal coming from the transmitter, like the carrier wave of an AM radio station. That is extremely narrow bandwidth and low entropy. And FM's not, well, there is a carrier wave, but it's not a huge part of the power of the station usually. And so the FM's more spread out. Now an AM broadcast would be easier to get. And back in the days of analog television, that was transmitted with the video transmitted on AM and the audio transmitted on FM. But the video had an enormous carrier wave, and those could be reasonably conspicuous across interstellar distances because you could tune to a fraction of a hertz bandwidth instead of the 150 kilohertz you have to listen to FM radio. And so that kind of signal would be detectable with modest improvements over our current technology, I believe, across interstellar distances.
Now, so isn't now TVs mostly cable or satellite, I suppose?
It is, and broadcast TV now uses digital techniques that put a much higher entropy into the signal. And so there isn't that strong carrier wave anymore.
Yeah.
Whoops, we lost Scott again.
Hmm.
What you doing, Scott?
So you have to search for a whole range of frequencies as well. I mean, have you heard? You're reminding me of some axion searches these days. An axion is a hypothetical particle that could explain some properties of charge of antimatter matter balance sort of thing. But and people have searched for these particles, but it seems that if they exist, they're extremely light and extremely weakly interacting. But they can couple to a pair of photons, which means that an axion can come along and convert into a photon in the field of a nucleus. Sorry, the other way around, a photon comes along, converts to an axion. The axion travels through a brick wall or a lead wall, and then converts back to a photon on the other side. So they call it light shining through walls. So they're looking to see if they can see actually, photons apparently going through a thick wall of absorber, but in practice they convert into an axion and then back out the other end. So anyway, that's an interesting sort of experiment.
To name these particles.
Axion, AXION.
But who decided that that's what it was going to be called?
Oh, probably the first theorists who wrote about this possible particle was explaining.
So its name comes from a popular laundry detergent.
Right. Yes, exactly.
And it was assigned to the particle by some theoretical physicists who thought that it would help clean up their theories. I'm not exaggerating.
That's true.
You have to have
I was wondering, how do you get these names?
I believe it's an axial vector field.
That's
right. Also,
so that's a technical term in physics. We have ordinary vectors, and then we have axial vectors in
change
vector analysis.
In a mirror, right?
Yeah. So
photon is an axial vector, actually. Yes.
So can we begin to think about some of the topics that we were working on? One of them, again, is this coronavirus thing and the vaccine that has been touted recently. And I know Abby has had several articles that she's been involved with and a lot of discussions, and I've been following her on Facebook. Abby, would you like to say something about this new vaccine and what the probabilities of us all getting inoculated are?
Okay. Now, when Joanne generously says I'm involved with them, it means I'm reading the papers. I'm not doing the research. But I'm talking about this stuff because, well, it's wicked interesting. What it comes down to, I mean, there are lots and lots of vaccine candidates in various different stages of being researched. And the two that are kind of coming around the bend first are both, the Pfizer one and the Moderna one, and they're both based on messenger RNA or mRNA, which is a brand new technique for making vaccines. What it comes down to is your traditional vaccine, however it, whatever details there are in it, it basically comes down to exposing you to a very mild or even dead form of that disease, whatever it is, so that your immune system is able to learn about it, and your specific immune system basically learns how to make antibodies for it. And once you can make antibodies for something, you're probably going to live through being exposed to it, because antibodies are cheap and can be made by the thousands. And so that means that if this disease-causing microorganism gets into your system and you already know how to make these cheap antibodies, you can just throw 10,000 antibodies at it and it won't have a chance. So that is how vaccines work. It's also how immunity works in general, specific immunity works in general. Why those of us who are as old as, in fact, I am, or John is, and probably some of the rest of you, if you had stuff like the mumps when you were a kid, or the measles or whatever, you're immune to them because you had that stuff. But it's the same principle as vaccines, that once you are exposed to a disease, if you manage to live through being exposed to it, then you're immune to it because your body knows how to make antibodies for it. And an easy way to live through your first exposure is by getting a vaccine rather than by getting sick, which is a whole lot worse. Having experienced the mumps, I will vouch for this. So that is how your traditional vaccine works. What mRNA vaccines do is slightly different. What they do is that they take a chunk of messenger RNA from the virus, and they expose your cells, not all your cells, but some of your cells to that. And then those cells, and they're actually cells in your immune system, and I am not quite sure how they managed to be so specific about it, but basically your cells make particular antigens that are what your immune system needs in order to figure out how to make those antibodies. You basically need a target. And so your own cells will express this little bit of viral, I think it's a viral protein. But the point is, what'd you say, John?
It's a piece of the spike protein.
It's a piece of the spike protein. Okay, so they express this viral protein. And then your specific immune system essentially says, oh, that's a bad looking thing. I should back up and say that your immune system is very simple in its outlook on life. There is self and there is non-self. Anything that is made by your body that is clearly a part of, your personal genome, it thinks is just fine. On the other hand, anything that is not self is deemed to be an invading microorganism and ought to be killed. So anyway, your own cells express a little teensy bit of the spike protein from the virus, and that is how your specific immune system learns to make the antibodies that target the spike proteins, so that should you then be exposed to the COVID-19 virus, SARS-CoV-2, you already know how to make the antibodies to kill that virus. And it's actually not so much killing it as tagging it and taking it out, and then other parts of your immune system go along and eat it, kind of like Pac-Man, if you ever played the Pac-Man game. So that's basically how mRNA vaccines work. It's never been done before. It has the potential to be very effective, which is why they are talking about 90% effectiveness, which is pretty remarkable. So we'll see. The unfortunate news about that is that the mRNA vaccines require super cold temperatures to be transported. Your everyday vaccine has to be refrigerated, which is why vaccination campaigns in developing countries always kind of had this stumbling block of keeping the vaccines cold. But there is a difference between refrigerator temperature and, dry ice temperature. And a lot of vaccines are transported just by having, a good container full of dry ice. But these are at lab freezer temperatures. These are super cold temperatures. You might be able to do it with a canister with liquid nitrogen in it, but it's that kind of cold.
But they must be made to room temperature to be injected. So they must survive for some time at room temperature. Is it hours or minutes or what?
I don't know how long it is, but basically you have to build a very technical cold chain. And I mean, you know, biologists are used to building cold chains. It's something you do even if there's some blood samples that you're interested in. You know, there was a researcher I know who worked on hepatitis B and collected blood samples from all over the world. And part of what he had to do to get them back to his lab in Philadelphia was basically have drops of dry ice along the way. And basically when the blood samples came in, he needed to collect them, stuff the container full of dry ice again, or have somebody do that, you know, stick them back on a plane and off they went. So the point is, biologists are used to the ideas of cold chains. But in this case, it has to be a super cold chain. And, you know, that's not, in science, as you all know, there's a difference between difficult and impossible. But you have to figure out how to do it. And it is going to mean that people in cities like Boston and Chicago, where there are major league hospitals and major league research facilities that already have super cold freezers, those populations are going to be at an advantage in getting this vaccine. Though you could build a cold chain to get it out to further populations, you know, using liquid nitrogen or, you know, putting super cold freezers on trucks that just run all the time and doing it that way. You know, as I said, there's a difference between difficult and impossible, but, well, this is where you need experts and competence and things like that, that we hope that will be valued in the near future. I'll just put it that way.
Well, let me comment here because, you know, the Large Hadron Collider, for example, is kept at less than 2 degrees above absolute zero, right, with liquid, actually superfluid helium. Now, we use cryogenics, where we've got a lot of expertise in that, but what I don't think they've addressed is the issue of making cheap cryostat containers, you know, that can keep stuff at minus 100 degrees and mass produce them. So, you can keep, you know, suitcase full or trunk full sizes of this.
Well, helium and nitrogen are completely different games. You know, the lab I used to work with at MIT would just ship liquid nitrogen in these big 160 liter containers, and we had so many of them around, we had to keep oxygen sensors activated. By the safety people made us keep oxygen sensors around because they were afraid that all the nitrogen boil off would suffocate us.
Yeah.
And so, yeah, around here in the Boston area, liquid nitrogen's cheaper than bottled water. Now, I don't know out in the heartland, you know.
But right, John, I agree. But to make cheap containers that contain, you know, a dose of this vaccine or whatever, and send it to Africa on a plane, because when you've got a good insulation, you don't need to have, you know.
No, that's a fascinating idea. Absolutely.
You'd be surprised at how good the thermos bottles you get for soup at Kmart are for storing cold things. They're really pretty good.
Mm-hmm. It shouldn't be such a big issue if it has to be kept that cold for shipping to Africa or wherever, you know.
Yeah. Well, of course, part of it is when we have to keep stuff cold. What we do in my business is we just, you know, keep a lot of liquid nitrogen around.
Mm-hmm.
Because it's quite cheap stuff. It's not that hard.
Right, but you're in one.
But there's you know, it's a different logistics from a normal vaccine, and scaling anything that's different up to 1 billion doses is going to be a challenge.
Right. Although I'm loving Michael's idea that, you know, if there is some essentially small, super well insulated box where you really could keep something that cold just by way of insulation and maybe some liquid nitrogen or something like that, you know, how long could you keep it cold for? You know, what's your target? Is it a day, a week?
A week probably is good enough for most transport. A week, I mean, you can send stuff around the world anywhere in a week, right? So a week,
it's not terribly challenging to make a thing that you can hold on your lap that will hold a liter of liquid helium for a day. Liquid nitrogen is a lot easier because it has a much higher heat capacity, so that you don't have to worry about heat leaks so much.
And liquid nitrogen likes to stay inside the vessel, whereas the helium just
helium is terribly treacherous stuff.
It's like roaches.
Joanne, that's only when it's superfluid. It's not necessarily, you know. Yeah, okay.
Well, the other problem with liquid helium is that what it tends to do is it tends to, if your fill tube is exposed to air, the helium tends to suck air down into the fill tube and freeze it. And you wind up with a plug of frozen air in your fill tube. And then as the helium boils off under this plug, you can have your device explode.
I was just going to say, yeah.
It actually happens at the LHC, right?
It gets exciting.
Yeah.
When they first did the arm,
I remember one night when I was just an undergraduate student, Doug Kleinman, who was a famous infrared astronomer, came in. Do you have a jobber length electrical drill that I could use? Because he had a helium doer that he was afraid was about to explode.
When they first switched the LHCR, they had a problem because there was a leak, and actually helium burst out, and several of the superconducting magnets were thrown around the tunnel. I mean, they had to stop everything for a year and go round through all these connections again. You know.
Well, yeah. If your superconducting magnet quenches, of course, there's a huge amount of energy that gets released.
Mike, could you turn your volume up a little?
Right.
Yeah, you're pretty quiet.
Am I? Oh well, I have to be closer then. I don't think I have a volume.
It's a little hard to hear you.
Is that better? That's probably better.
Yeah.
Yep.
Okay.
I had a clarifying question I wanted to ask you, Abby. When you say it's 90% effective, does that mean that it would kill 90% of the viruses that come into a body? Does it mean that it's 90% of people who are inoculated, or does it mean something else?
That means basically, I'm trying to remember, actually. I think I'm going to pass on that one rather than say something wrong.
Okay, well, we can look that up.
My guess is that 90% of the people who get the vaccine don't contract it, but 10% still will.
I suspect as well, which is actually very high coverage. I mean, at that point, you are looking at the much misused term herd immunity, which in real life means that if you have a big vaccination campaign, then for the, let's say, 10% of the population for whom the vaccine doesn't work for one reason or another, their bodies don't learn to express the appropriate antibodies. There are so few people around who contract the virus and carry it that they are unlikely to be exposed to it. That's what herd immunity is in real life. And that comes about through massive vaccination campaigns. And it's particularly worthwhile when you do have a vaccine that is highly effective, because it just means that most people will be fine, and that very small portion of the population that, you know, is still susceptible to the disease basically is not likely to come in contact with it if they are in, you know, a vaccinated population. They may have to worry if they travel to less developed countries, but that's always the case.
I have a question.
Well, I'm reminded of the herd immunity that Europe gained with the Great Plague. 1/3 of all of Europe died, and they achieved herd immunity. But it was a terrible way of doing it.
But only for the people who lived through it, and all of the people who were born after that didn't have that immunity.
Yeah.
That's really not
I have a question about this virus. When you're infected, where is it located in? Like just in the blood, or in the blood plasma, or in the flesh? where or everywhere through the body? Is it localized somehow in the body?
What it are you discussing?
When I get infected by COVID-19, for example, so these viruses are in my body. Where are they located in particular parts of the body? Or in
the virus is actually pretty awful that way. This is one of the reasons why people get so sick, is that the virus actually invades cells through two different receptors. There's the ACE2 receptors, and there's another one that had another receptor type. I don't remember its sort of alphabet title. But the point is, those receptors are present on lots of different kinds of cells. So for instance, the ACE2 receptors, you've got them in your nose and you got them in your lungs. You also have them in the linings of your blood vessels, both epithelial lining, which is basically like the little silk lining on the inside, and in the muscles in your arteries. And that means that since basically your blood vessels are everywhere, it means that potentially all of your different organs can be susceptible to this virus. It, apparently can get into your brain, and it does a number on people's kidneys. And John Doty is now going to laugh because I'm going to get onto one of my usual topics. Yes, it invades the testes, or I should say, when I say it invades, I'll put it another way. There are ACE2 receptors in the testes. So basically, any cell that has an ACE2 receptor is susceptible to this virus, and that is why the conditions that people get are so widespread. And the reason why it was thought to be a respiratory disease in the beginning is, first of all, because, of course, we inhale the virus. That is usually how people get it. I am told repeatedly you can get it through your eyes as well. But, if people inhale the virus, of course, it is going to wind up attaching to the blood vessels that have ACE2 receptors that are in your lungs, because your lungs are absolutely packed with blood vessels. Yeah. But that's also why digestive problems like diarrhea are a common part of a COVID infection, but not a guaranteed one. This is the thing, is that it's kind of weird how different people will have different symptoms. And, a whole host of effects, and it just has to do with which particular ACE2 receptors the virus winds up getting at. And I don't know if we have any particular knowledge about, why some people wind up having kidney effects and other people wind up having brain effects and other people wind up having heart effects.
It's interesting.
All of those things are in principle susceptible.
Okay. So in principle, you could get it from a blood transfusion from somebody who's infected. That could give it to you, right? Is there any data on that?
Okay, well, I was talking about blood vessels. When I say blood vessels, I'm talking about the tubes.
Okay, I see. So it's not like floating around in the blood. So,
well, I'm not sure whether it is or not. As I said, that's something I'm not certain about. I'm telling you the cells that it attacks, which are, as I said, cells with ACE2 receptors, which includes, as I said, the linings on the blood vessels. Okay. I assume that it will be floating around in your blood, but I can't guarantee you that.
So a news story from November 1st says that it is not yet known whether COVID-19 can be transmitted by blood transfusions.
Okay, thanks.
Yep. Also, a piece of news, the 90% means exactly what you thought it meant. It means that 90% of patients who are treated respond and create antibodies that protect them.
Okay, great. Thanks. And getting back to what you were saying about blood, actually, though, that's one of the things which is a real problem, as it turns out, is that it causes all kinds of blood clots. And once you get blood clots, suddenly you're getting secondary problems of strokes, heart attacks, pulmonary embolisms, and things like that, which are genuinely attributable to the COVID infection, even if what you wind up dying of is a stroke. And there's been some fairly unfortunate data, even from fairly young people who were infected with COVID, who wound up sustaining heart damage. And in some cases, they didn't even know it.
We tend to think of immunity as a binary thing, like I'm immune or I'm not, but it isn't really that way, right? It's you have some sort of immune response.
Right.
So people will say, well, I've had the disease, so I'm immune, or they'll be immune for some period of time, but it's not a binary where it suddenly you drops to being vulnerable, right? So that makes me wonder about children.
It depends, by the way.
Yeah.
It's biology, it depends.
So with I know we don't know very much about how it affects young, children, but could it be that their immune system is just much stronger and therefore they have immunity in some sense, or they may not have immunity, right? It may just be that they don't get the symptoms. Do we know that?
I am not certain why the age differential is the way it is. I mean, we now know that people of any age can get it and can suffer from it. But why?
There are different systems, and the antibody system is one system. When you are young, especially, you are more dependent on the interferon system because your antibody system hasn't yet been trained. And the interferon system is not specific to particular organisms. And the stuff I've been reading lately suggests that the difference between a good outcome and a bad outcome is highly correlated with how strong an interferon response your body comes up with.
That's one of the forms of general immunity. General immunity is basically, again, non-self is bad, go attack it, but without the specificity of antibodies. So that's interesting.
Go ahead.
So a question also, the yes, no, are you infected or not? Because I presume there's some threshold. I mean, I imagine if I'm in a shop where somebody is infected, I can breathe in and I've got some of the viruses in me, a few of them, but not enough to consider myself infected. I suppose, it's only when they become more than a certain number over some threshold that you say, now you're infected. Is that correct?
Well, the way there's been a lot of discussion of what's called viral load. It's the kind of thing where, in principle, if you had a completely unprotected system and you got one virus and it invaded a cell, you could presumably wind up with an illness because that's the way that, doubling works. You have one virus that then results in, 10 or 100 new viruses and on they go. Exponents being what they are, you could conceivably get full-blown COVID from one virus, but we have immune systems. Yeah. And so even when our specific immune system has not yet been trained up, we still have a general immune system, as John was saying, which has a bunch of different components. There are a bunch of white blood cells that will eat anything in sight, and there's interferon and other things like this. So, you may get lucky and that one virus winds up being, knocked off by a white blood cell and you're fine. The problem indeed with most of your protective systems is the problem of being overwhelmed. That, you can overwhelm some biological protective system and then, whatever it is gets you sick. And as an aside, this is also what I explain to people with the other protective mechanisms in the lungs, even for things that are not microorganisms, but things that are just detritus in the air and all of this kind of stuff, that we have this whole system of mechanisms. I won't call them filters because they're not, though they act that way, but we have this whole system of mechanisms for keeping crud out of our lungs, basically. And they work pretty well and they're pretty cool. But you can overwhelm those systems if, for instance, you work in a coal mine and you don't have proper respiratory protection. You wind up getting black lung because so many particles of coal dust get in there that your system can't get rid of all of them. So with lots of biological systems, they're really pretty good, but they're not going to be foolproof. You put enough of anything into a protective system, you can probably overwhelm it.
So there was a little bit of discussion amongst us here a few minutes ago about developing an immunity, and then you're good. That's it. I know that in some cases you can get a vaccine and you don't have to get any booster shots. The vaccine essentially programs your immune system and you're good indefinitely. Other vaccines that deal with other pathogens, you do have to get booster shots.
Right.
And then there's the third option, which is the viruses are so simple compared to bacteria in terms of their genetic programming and whatnot, that they can experience a very high mutation rate. And some of those mutations could thwart an otherwise programmed immune response. So maybe you can speculate about some of those topics.
Well, that's kind of why there's a flu shot every year, is that is basically where epidemiologists are taking their best guesses as to which mutations, which new genetic lineages of the flu are likely to be prevalent in, several months' time or umpteen months' time. So this is why the flu shot is also never perfect, because epidemiologists have to guess as to what the prevalent strains are going to be many months in the future, because it takes time to manufacture a vaccine. And so they want the vaccine ready in time for flu season. So they have to, as I said, kind of make their best prediction as to what they think the prevalent, essentially newly evolved forms of the flu are going to be by the time flu season rolls around. So as I said, you get your flu shot because those are the latest versions of the flu that are out. And with any kind of luck, people made a pretty good prediction about it. But yeah, so as I said, that's why we always need a flu shot. What I have read, and so, it might be one of these things where we have to get, an annual COVID shot in the future. But I have also read that coronaviruses tend to be a bit more conservative that way, that they tend not to mutate to that degree. And I mean, we've already experienced some mutations in the sense that we can now tell whether people got infected. This is kind of amazing. I was reading about this just the other evening. We can now tell if people got infected, for instance, from the version of SARS-CoV-2 that was present at the Biogen conference in Boston back in late February, which is known to be a super spreader event now. We can actually tell just by looking at genetic lineages sort of who wound up getting that version, and the answer is a whole lot of people. That said, apparently that does not really make it a new disease where we would need a different vaccine for it. My understanding is that coronaviruses, as I said, are a little bit conservative that way, so that that may be a bit of luck on our side in terms of not needing, continuous updates to the vaccine. Now, how long the immunity that the vaccine induces in us will last is something we simply don't know. It's a brand new disease and brand new vaccines, and so we just don't know how long the immunity will last.
Aren't they saying that this is going to be a shot and a second shot like 3 weeks later?
For the mRNA vaccines, yes, it's going to have to be 2-stage shots. There are other vaccine candidates coming along that may also be very good, that may be one-shot deals, and they may not need super cold storage. You know, as I said, it's still early days in terms of what's coming online or what appears to be viable as a vaccine. So, you know, we're hearing about the mRNA ones first because they're kind of the first ones around the bend looking like they're doing well. But there are a lot of other things that are possible as well.
So, Abby, I have a question as a physicist about the physical properties of this virus. And I don't know what experiments have been done on that. I'm sort of imagining a thought experiment where you get the virus and you have it in the lab and you irradiate it with electromagnetic radiation of different frequencies. You see if there's some resonant frequency that causes it to blow itself apart, something like that. Can one destroy it with electromagnetic radiation of a particular?
Well, you can destroy it with a UV light.
UV light, it does it. Now, does UV light have to be a particular narrow frequency, or it can be anything? I mean, so.
That I couldn't tell you, but I do know that microbiologists and doctors, you know, among my acquaintances, have said that, you know, although this is probably not useful the way it's being, I'll back up. One could probably set up something where if you were worried about, say, your mask and you wanted to disinfect your mask, if you did a good job, you could set up a UV light, put your mask underneath it, and it could get disinfected. But, you know, with UV light, you have to worry about shadows and all kinds of other things like that. But in principle, UV light kills these things. And if you could figure out a way to do it right, it might be effective.
So if it was a particular narrow frequency of UV light, but you could imagine so that you irradiate the air in shops with this UV light that kills the airborne virus without affecting people. If it was not too intense,
except for all the shadows.
Well, the UV light sort of irradiates the air around. I mean, of course.
Yeah, usually the biological effects of UV are not resonant effects. They're photoelectric, where there's a threshold frequency.
Yeah.
And if you're above the threshold, the photon liberates an electron, and the electron is actually what damages the RNA.
Right.
Okay, cool.
So I've been following some UV masks that have been developed. So the idea is you put a long wavelength UVC LED into the mask. Then the next thing you have to do is find a way of having the air spend enough time in front of this UV light that the UV light can sterilize the air. At the same time, you need to make sure that it doesn't leak any light, because you don't want UVC hitting your skin.
That's what I was thinking, right, yeah.
So there are masks that are out there being developed, and I've actually ordered one. So I don't know if I'll ever receive one. It was on Kickstarter.
It's not really a bad idea, yeah. I mean, for medical settings where you have people wearing essentially what amounts to like space masks, that would be one way of doing it, sure. Now you need to have a power source at all times, I'm assuming.
Yeah, it has a rechargeable battery, lithium-ion battery inside it.
But so basically, you're sterilizing the air as it passes through this airspace, and then you breathe the sterilized air.
Right, and the reason they're using a longer wavelength of UV is so it doesn't create ozone. Otherwise, you'll just be breathing ozone the whole time, which is not good either.
Yeah, you need to think of that.
I have a friend, another physicist, who is a co-owner, co-developer in a small company that is selling UV sterilization, bulk sterilization equipment to hospitals. And it's been a few years since I talked to him about it, but my my memory is persuading me that it might be something that was installed in the HVAC system, something like that, so that the circulating air is more purified or purged of susceptible pathogens.
Well, airplanes are using HEPA filters and that kind of thing, and they say that essentially there is no potential of contamination.
Mm-hmm.
Yeah, I read recently the air in an airplane is safer than the air in the terminal building or something like that. Yeah.
Interesting. That's really good to know. We do have a question from one of our YouTube viewers. Several viewers stuck with us through our technical challenges at the beginning. The question is, this viewer heard that there was a theory that the descendants of the Europeans who had experienced or contracted the Black Plague and survived, that those descendants are less likely to get sick, which is, or less likely to get sick from the Spanish influenza specifically. Anybody have any knowledge about that?
Well, it seems to the Black Plague, I think we're probably all descendants of Black Plague survivors, right? If you look at the statistics.
Yeah, European descended people, yeah.
If you're from European descent, as we all are, the chances are very high that we're all descended from survivors of the Black Plague. So I don't know how you can prove that or disprove that, really.
Well, I know my parents going back that time did survive.
Yeah.
In the Spanish influenza.
All our ancestors survived the Spanish flu, right?
Well, at least they had reproduced before perhaps succumbing.
Before they died of the flu, right?
The Black Plague, that killed a third of the population of Europe, didn't it? Something like that.
Yeah, it was terrible. But I don't know what it was like in Scotland. So, you get up into the Helands up there, and, what can survive up there other than a Scot?
Cows, the long-haired cows, right? Up there, yeah.
So, Abby, one of the other things I've heard is that the coronavirus as a category of viruses are related to the common cold viruses, and that some people who have had several different strains of the common cold may have acquired at least some sort of boost in immunity, natural immunity to COVID. Is that just pseudoscience or what?
Well, there's two roughly different kinds of viruses that might give you a cold. One is well known as the rhinovirus, which basically means the nose virus. But there are also some colds are caused by coronaviruses. Those are actually different kinds of viruses. But I can see how, in principle, if you happened to have had some colds that were caused by the cold-causing coronaviruses, that your body would have a little bit of experience with dealing with coronaviruses. So it's an interesting thought. I mean, there was also some research going around, or a suggestion going around a few months ago, and I don't know how it has panned out, that the MMR vaccine might actually confer some immunity to COVID-19, which could account for the differential for the age differential, because the very old are the people who didn't get the MMR vaccine because it hadn't been invented yet. So as I said, there was, let's just say, a correlation had been noticed, but I don't know what further has been done on that.
I would also comment that in answer to the question, the immune system is, after all, a product of your genome. And the programming of the immune system is in part due to what you've inherited, not merely which pathogens you've been exposed to. And so Europeans who had been exposed for hundreds or thousands of years to the endemic diseases in Europe were the product of natural selection for people who had immune systems that resisted those particular diseases. Now they show up in the New World, And those people haven't had those generations and generations of natural selection for immune systems capable of dealing with those pathogens. And yeah, they died.
Right. Well, that's why smallpox was so devastating to the Native Americans. I mean, smallpox was bad, but it was much worse for Native Americans. But this is also one of the reasons why epidemiologists, when they saw SARS-CoV-2 developing and, jumping from animals to people, they knew that we were in for a bad time, because now this is where you get a little bit more into evolutionary biology, but basically immune systems kind of co-evolve with the things that frequently infect them. So this disease that appears to have jumped, I forget what it was, from like pangolins to bats to humans. I've actually looked at like the family tree of the SARS-CoV-2 virus, and it kind of, breaks off, branches off from from other coronaviruses. And there's sort of a pangolin version of it. And then there's a bat version a little further out, and then there's the human version that we got. But the point is that the pangolins, there are other animals that have been infected with viruses like this before for so long that their immune systems have evolved to the point where the virus that kills us, their immune systems have evolved to deal with it, and they might get sick, but not horribly sick the way we do. And this is one of the problems when you have a disease that makes the jump from other animals to people, is that our immune systems have not had generations of coevolution in which to learn how to deal with the disease. And so it jumps onto us, and our immune systems are much less prepared than the pangolin immune system or the bat immune system.
So that's
why it's ripping us apart so much.
That leads me to something that I have learned in the past couple of years about our DNA, and probably the DNA of every extant species. But if you remember back in the early 2000s or so, soon after the Human Genome Project, there was all this talk about junk DNA.
Yeah.
And one of the major contributors to the so-called junk DNA, and by the way, a lot of it that was previously thought to be junk is quite functional and necessary. But aside from that, there is some sort of baggage that just sort of comes along with the human genome and reproduces from generation to generation. And a lot of that baggage, a lot of that tag-along genetic material is thought to have been derived from prior viruses that ran rampant in the population until the population developed some immunity.
Yeah, no, there are chunks of viral DNA and RNA kicking around in our system, in our genome.
So it seems to me, is it true that, a virus can mutate so that this one can mutate to something different, sufficiently different? And obviously, if there's a certain probability that a virus will mutate, the more there are around in the population, the more likely it is to have a mutation. So with billions and billions of viruses circulating now, the chance of a mutation into some next version, which could be even worse, is getting higher and higher the more people are infected.
We'd be better off with this thing being in smaller numbers, yes.
Right. So the faster we can dampen it down, the less chance there is of having another virus coming along in 2 or 3 years' time that is going to be even more devastating.
That's a very good point.
Yeah.
The person who asked the question on YouTube is clarifying it. They said by contracting the plague, this person, I don't know whether it's a he or a she, but this person specifically meant people who had contracted the Black Plague and then survived, and thus may have passed along some enhanced immunity to subsequent generations. So, but I think Black plague still breaks out every year. There are cases in the United States, there are cases in Europe and Asia. But one of the things about the Black Plague, if I'm remembering correctly, is that it responds very well to antibiotics. It's not a virus, it's a bacterial thing. And so modern antibiotics can sort of nip it in the bud.
Mm-hmm. Yeah, there are.
Well, let me comment on the heritage part. Evolution works negatively. It's not that the people who survived passed something on to their descendants because they'd had the Black Plague and survived. It's that the people who didn't survive because their immune systems were not capable of coping with the Black Plague didn't have descendants.
Thank you.
So what happened was the plague weeded out those people whose that genetic background that made it possible for it to infect certain people, but worse than others. And that's how evolution works. It works negatively. When someone is prevented from reproducing, their genetic makeup does not survive to the next generation.
Yeah, just because I had chickenpox as a child doesn't mean that my children are immune to chickenpox. They have to do it themselves. Whereas again, things like the Black Plague, well, I happen to be of the genetic makeup that survived it. Now, I don't know if I would again, because there's been so many generations and so much going on that I might be just as susceptible as the next person. But then again, I might not be.
Right. But as John pointed out, when it comes to something like surviving the plague, those who didn't survive, well, didn't have descendants. And so that's how that got weeded out. And in general, now, I mean, I will back up and say that epigenetics is showing that this is not always completely true, but in general, acquired characteristics are not passed on. If you dye your hair red every day of your life, your descendants will not have red hair because you used all that hair dye.
Another point about John's argument is that the young people are more likely to survive. The ones who die have probably already had their children, right? So
I didn't hear what you said, sorry.
Well, the death rate is higher among older people, the older people who've already had their children. So
right.
they don't come into that equation.
Right.
This negative inheritance is working for people who died before they've had a chance to have children. And the young are more immune to die, less likely to die from it.
Well, for COVID, yeah, but we're talking about evolution here, and that takes generations.
Yeah, right.
Now the truth is, yeah, it looks. I would guess that coevolution between humans and COVID will take longer than for other diseases, precisely because it is the old that it kills. Yes.
Or preferentially kills. It can occasionally kill young people, but not often.
Yeah, and there are elderly people that certainly survive as well.
Mm-hmm.
Yeah. Just recently, there was a fellow who'd been in the hospital for 600 days, 70 days or something, who finally, after all the therapy and else, he finally walked out. But wow, what he went through.
Yeah.
Yeah, and being able to walk out of the hospital and being fully healed are two completely different things.
Yeah, we're hearing stories about people who still have deleterious effects that persist after their viral load has reached background or non-detectable levels.
Right.
We're tending to think in our cultural environment that when you think of a refugee camp where you have 100,000 people crushed together in a camp in tents and so on, they can't distance, they can't wear masks, and and this is happening all over the world.
Yep.
And then I was hearing about horror stories in Spain where the culture is to have a maid who comes from Mexico or some poor country, and they've been stuck in the home since March. They're not allowed out, or if they go out, they're fired and left homeless on the street. It's really a horrific situation. I think we're pretty lucky here where we are,
Absolutely, no doubt about it. I mean, we can complain, but our complaints are not life and death complaints. I mean, we have to be careful of life and death situations, but we can protect ourselves to a degree that many, many other people can't. And we, looking at the people here, can live fairly comfortably throughout all of this. So there are a whole lot of people who are where it is affecting them far more than it's affecting us. Absolutely.
Yeah.
Yeah.
I, for one, am out in space, so I can't be harmed.
Right, that's true.
You've got a goldfish bowl over your head, though. I don't see that.
So we got a little break here in the topic. I thought I would mention, since I didn't get to it at the beginning of the program due to technical difficulties, that you've tuned in for Sidewalk Science, which is a program that happens about twice a month. It habitually happens on the Saturday prior to the first Sunday and third Sunday of any given month. So occasionally you might find that it only happens once a month or 3 times a month. We are supported in part by a grant from the American Humanist Association and from the local humanist group here in the Chicago area, the Prairie State Humanists. Joanne, Mike, and I are all members of the Prairie State Humanists. And Abby, I wanted to congratulate you for recently being elected to the board of the American Humanist Association.
Yeah, thanks.
All right. Let's see. I wanted to give Ivan a chance also. Ivan, I don't know if you saw my email from earlier, but I just sort of throw the door open and see if you had any science or philosophy of science topics that you'd like to delve into a little today.
I don't have anything specific that I plan to talk about. I was reading an article about philosophy of science. So there's I guess I don't want to open the door too wide. There's so much to talk about in philosophy of science, but you may have heard of Popper's criteria for a scientific hypothesis is one that can be falsified. And it turns out to be very simplistic because most hypotheses you can alter in subtle ways to avoid having them be falsifiable. So you can always say, well, neutrinos, they aren't massless, the mass is just very small. And then you'll do some experiments and then rule something out, and then it's we'll still make it smaller and smaller, and it becomes effectively unfalsifiable because you can always push it beyond the limits of the experiment or come up with some other auxiliary hypothesis. So the philosophy of science is really pretty tricky. That it would be nice to have a nice simple statement about what constitutes a scientific hypothesis, but it turns out to be rather difficult. And there are Thomas Kuhn wrote a famous book about scientific revolutions, in which he describes normal science, where you have well-defined hypotheses and you're doing very clearly defined tests between different theories, and what happens when you have a crisis and the theories no longer seem to be satisfactory, and then things move in a very different way. It's not just one theory against the other in some experiment. It tends to be you switch to a new paradigm, and in the new paradigm it's not so simple to see that, oh, you did some simple experiment and it went from one to the other. It's really like you redefined all of your terms. So I'm not going anywhere here. I've just been reading some very it's a very rich topic to talk about, and maybe for next time I'll prepare something to talk about on this subject.
All right.
Well, it brings up the thought about Friday the 13th, and that is an interesting hypothesis. continues to go on and on and on. And as a philosopher, what would you have to say about Friday the 13th?
What do you mean, Johan?
Well, there's
every 7th month you have a Friday the 13th.
But it's supposed to be terrible, and it's bad luck, and you know, hide inside and watch out for black cats.
Is there any science behind that, Ivan, to your knowledge?
I'm going to bet that there is some, but I've never heard of it. It probably just says that I mean, how would you test it, and how would you for example, what is the scientific definition of unlucky?
Good point.
Because you could always set up an experiment and say, okay, we're going to look at radioactive decay from some sample and see how many of these decays. But radioactive decay is stochastic, but it's not unlucky, right? So how do you define luck?
You could do a sociological experiment, I think, on that. I mean, you could ask 10,000 people to say, what was the unluckiest thing that happened to you, the thing you thought most unlucky to happen to you, if you remember the date, not the date, but the date. Okay, you collect all these things, and then you make a histogram of Monday, Tuesday, Wednesday, Thursday, Friday, and see if Friday statistically sticks out as having more unlucky things. You could do that.
There are all kinds of correlative studies that have been done about that. For example, it's more likely, if I'm remembering right, I might be getting the day of the week a little wrong, but if I remember correctly, it's more likely to rain on weekends than on weekdays, because the particulate matter emitted by vehicles during people's weekly commutes build up, and then some of that particulate matter forms the little nucleation particles around which snow and rain form. And towards the end of the week, on Fridays and Saturdays and Sundays, it's slightly more likely to precipitate than during the week. And that correlative study about specific effects on the day related to the days of the week have often underlying social or cultural aspects, like when we're hitting the road. So for Friday the 13th, for example, there may be a subset of the population who becomes especially anxious around Friday the 13th. And maybe they're more distracted when they're driving, or maybe they're, you've heard about the idea of self-fulfilling prophecy. Maybe there's a statistically non-zero chance that somebody who's already worried about Friday the 13th will be distracted by this or some other way be careless. And but it has nothing to do with astronomical events or the particulars of the calendar or anything.
Well, we were taught that it was actually to do with the Last Supper, when you had 12 disciples and Jesus at the table, and it was Good Friday, and it was unlucky for Jesus because
it was the Templars. It was the Knights Templar. So when they came down hard on the, I forget the name of the leader of the Knights Templar, it was essentially a purge. It was what? Demolay, yeah. There was a purge that happened when the Knights Templar were outlawed, and this took effect. There were a lot of assassinations and whatnot, and arrests of Knights Templar on on a particular Friday the 13th.
Well, the way to do it, of course, if you want to exclude this sort of cultural anxiety, is to do your epidemiological analysis based on data from a culture where 13 is not an unlucky number.
There you go.
Do it in Japan, where 4 is the unlucky number.
Right. I was just going to suggest that.
Okay. All right.
In Japanese countdowns, they don't use when you're counting down, they don't use the normal official number for 4, shi. They use yon because it would be unlucky. So you go go, yon. Oh man, I haven't been working in Japan for a while.
And it's as how some hotels in the U.S. don't have a 13th floor.
Right.
The Japanese will substitute yon for shi because she is bad luck.
Yep. And Japanese hotels often don't have a fourth floor.
Oh, interesting.
So, John, there's been an interesting news story this past week about fast radio bursts.
Oh yeah.
You want to tell us a little bit about that? I assume that you know quite a bit about it. Oh, nice cat.
This is the black cat.
Ah.
Lucky, huh? They're lucky,
I
huh?
like black cats.
They're lucky.
Well, there are a couple of magnetar stories that there's an object, there's a magnetar in our galaxy that has been observed emitting a rather wimpy fast radio burst, but it's associated with X and gamma ray activity. And yeah, the NICER mission that I'm involved with on the International Space Station has been doing the X-ray, it's doing some of the X-ray monitoring. And so that reinforces the idea that magnetars, which are extremely magnetized neutron stars, are the sources of fast radio bursts. And there's a hypothesis that the difference between the flares that produce X-rays and gamma rays and the flares that produce radio is similar to what happens with solar flares, where some produce just electromagnetic radiation and some produce coronal outbursts. And the thought is that if a flare on a magnetar produces an expanding plasma similar to a coronal outburst from the sun, that is the source of radio emission. This is all highly speculative, but we are making some progress and we are finding phenomena to study and correlate with each other. And yeah, it's getting interesting.
Yeah, another news piece of news I saw about neutron stars in the past week or two was that studies of gravitational radiation, also considering other sorts of radiative signals from pulsars, have shown that the deviation from perfectly smooth of a neutron star or a pulsar specifically must be less than the width of a human hair. In other words, it's so smooth that it doesn't have a dipole moment or a quadrupole moment to send off gravitational waves as it spins. And they've narrowed that down to the point where any deviation of the material, this is really incredibly dense material. They know that any deviation bigger than a human hair would have showed up in the signal, with the implication being that neutron stars, or these particular pulsars that are being studied, are some of the smoothest objects. They're the size of a city, and some of the smoothest objects ever found in nature.
They don't have hair, right?
Right. Neutron star, not only do black holes not have hair, which was a famous phrase made by John Archibald Wheeler, but neutron stars also don't have hair.
Yeah. So an easy way of thinking about these densities is the following. I always remember the following numbers. I use centimeters. So an atom, typically 10 to the minus 8 centimeters. The nucleus 10 to the minus 13 centimeters. That's a factor of 10 to the 5. So in volume, it's a factor of 10 to the 15, which is 1,000 trillion times denser. So the ratio of a neutron star to a normal star is like 10 to the 15 in volume.
It's easy to say 15, but the implication of that 15 orders of magnitude is mind-blowing.
And of course, an atom is mostly not electrons and protons and neutrons. It's mostly just empty space, but full of electromagnetic radiation. But the particles themselves are taking much less volume.
Well, yeah, it depends on how you look at it.
It's crammed full of electron wave functions.
Yeah. That's right. It's crammed full of electron wave functions.
Yes.
I was one of Victor Weisskopf's students, and he came up with the model of the atom, where most of the electrons in a heavy atom form a kernel, which is much larger than the nucleus. But because of the Pauli exclusion principle, it's almost impenetrable to the valence electrons. And so you can make an excellent model of a heavy atom by simply putting a few electrons around this perfectly exclusive, perfectly hard excluding kernel. But the kernel is much bigger than the nucleus.
Okay, that kernel is made of the electron wave functions that are impenetrable, right?
Yep.
Not the nucleus itself. But you always see diagrams of atoms in books where you've got a BlackBerry-like object with electrons just going around it like that.
Right.
Yeah, that isn't how it works.
I know, but there's even a NASA project for schools. You see those diagrams, and in fact, blow the atom up to the size of my room, and the proton is a pinhead in the middle.
Yeah.
I wanted to also mention before we close out some food for thought here about the Popper's falsifiability. It occurs to me, and it has occurred to many other people before and besides me, that, John, your experiments with astrophysics and the detectors and satellites that you build looking at astrophysical phenomena, and Mike, the detectors that you've helped build for particle physics, I suspect, and you can confirm here live on our broadcast, I suspect that neither of you set out to show that something didn't happen, that the Higgs particle did not exist, or that millisecond pulsars did not have a particular property. I suspect that you weren't looking to find disproof for a hypothesis.
Well, you see, a lot of people have different motivations. So if you look at all the physics papers coming out of the Large Hadron Collider in the last year or two, I mean, most of them are search for this, search for that, search for that, and putting limits, exclusion. We didn't see it with this mass region. We're excluding it here, excluding it here. Personally, I'm motivated by discovery. I want to discover something new, okay? But a lot of people, they put out proposals. We can exclude dark matter in this mass range, or we can exclude it in this mass range, which is progress to exclude things. But so many of the studies that are being done are actually, hoping to discover something, but realizing that more likely you're going to be excluding something.
Yeah, but you didn't build a giant experiment to look for the Higgs boson under the premise that you were really trying to disprove the theory of the Higgs boson.
Well, let's consider building the Heli-2 space mission, where when we started out, there were something like 100 different hypotheses for what gamma ray bursts actually were produced by. And our objective was to exclude 99 of them. Okay, it wasn't any specific 99, but we had, if we do this, if we make this measurement, we can exclude things over here. If we make this measurement, we can exclude things over here. I also remember a talk by John Bacall right after the neutrino result from supernova 1987A was announced. And this was a talk on the solar neutrino problem, where the neutrino flux from the sun was only 1/3 what theorists thought it should be. And he had this slide from a few months previous. And basically, then he overlaid it with a slide that crossed off many of the hypotheses, because the majority of the hypotheses for explaining the solar neutrino problem meant it would be absolutely impossible to see any neutrinos coming from a supernova.
Right.
And so it is true that winnowing out wrong theories is something that we do. Now, I've also been involved in cases where, I remember one case where we at MIT worked with Joe Taylor, the pulsar Nobel Prize guy for his binary pulsar. We had we had seen paper in the literature on a pulsar discovery that we didn't believe. And so we quickly made up an experimental, we realized that we could make up an experimental setup that would test this. And we did, the claim was that this thing was pulsing in the optical at the same, and we didn't believe that it was pulsing in the optical. We knew it was pulsing in the radio. So we got Joe Taylor to do our ephemeris calculations for us, and we arranged to do a stroboscopic experiment where we looked for what we did was we spread the pulsar time domain across a CCD and made it into a stripe, and we did it synchronously with the pulsations. And we tried it on the crab, and we got two little nice dots for the double pulses, where we know the crab does that. But we didn't think that this pulsar would do that, and lo and behold, it didn't. So we were able to exclude. We had much higher. Our approach had much higher sensitivity than the approach that these other folks had used. So we were able to exclude this result that we didn't believe, and that does happen. The other comment I would make, though, is that I don't know about this idea of falsifiability. When I'm actually doing physics, I am going to use whatever theory my experience and judgment says works. So if I'm dealing with gravity, I might use Galilean gravity. Gravity is downward acceleration, end of story. I might use Newtonian gravity, where gravity is a force. I might use relativistic gravity, where gravity is curvature of space-time. It depends on what, there are certain problems that are accessible to one approach and certain problems that are accessible to other approaches. In principle, general relativity can solve all your gravity problems. In practice, the mathematics is so difficult that you don't want to go to it unless the phenomena demand it. You want to use a simpler theory. And so there are these practical aspects. We use layers and layers of theory. I like to joke that no electrical engineer has ever used a consistent theory of electromagnetism to design an electric motor.
Right.
About falsifiability, John. I mean, okay, Newton's theory of gravity said every body in the universe attracts every other body with a product of their masses. You can never test that, of course, because you never do the experiment on every body. But you can find one example that disobeys it. You falsify.
Yes, and we have multiple examples that disobey it.
Yeah, and
that leads on to
So we have in that sense falsified it. On the other hand, we keep using it.
It works in a huge domain. It doesn't work for black holes and
that's right.
So Sean Carroll, the physicist whom I admire and listen to a lot of his material that he makes publicly available, has really advocated the idea of effective theories, which is exactly what you're talking about, John. There are different theories that are appropriate in different domains. You wouldn't use a theory of quantum mechanics to figure out cellular biology, for example, even though all of the molecules and atoms in a cell are just constructs.
Yeah, might if you're trying to figure out how a chloroplast works.
Oh, that's true. That's true.
Now, thoughts arise. I believe that's quantum mechanical at base. The fluctuations, quantum mechanical fluctuations generate thoughts at the bottom. Anyway,
maybe.
Are we supposed to finish what time? Are we over time? In overtime?
Yeah. Let us go a little bit over because we started late due to our technical problems. But just to wrap up this disprovability thing, one of the most famous statements about disprovability was something about finding the fossil of a rabbit in the Cambrian strata would serve as a great piece of counter evidence to Darwinian evolution, for example. So even theories that have nothing to do with atoms and neutron stars are still in principle falsifiable. And it's the in principle part that is important.
Yeah,
well,
somebody might have planted that fossil. I told you my story. I collected Devonian fossils when I lived in Devon. We moved to Sussex, and I buried them in the Wealden clay, which is a totally different stratum. I did being mischievous, but I got bored with the collection. And then I wrote to Richard Dawkins and said, oh, by the way, I have to admit, I buried these Devonian fossils in the Sussex clay, just in case somebody found them and forced you to worry about evolution.
Right. Well, we are at the bottom of the hour. We went over a little bit to account for the time lost to our technical difficulty, but we're meeting again, I believe, on December 5th, which is the Saturday prior to the first Sunday in December. So we'll see you again in 3 weeks, not 2 weeks. And thanks everybody for tuning in. And thank you so much to our panel of scientists and science communicators, and wonderful far-ranging discussion as usual. Thank you so much. Have a safe holiday for Thanksgiving, and
great Thanksgiving.
Happy Thanksgiving.
Be well, stay safe.